Hello, students. So, this is chapter 5. This is a fairly important chapter on light and matter and how light and matter interact. We already defined light in chapter 4 as a transfer of energy. It's energy that's moving from one place to another over long, not like through materials, but across space. The picture I have here is one of those interactions. You recognize the rainbow, um, but there's all these dashes, dark areas in it. That's going to be we're going to talk about spectrums, light coming from matter, or light passing through matter. So, first there's light. How do light and matter interact? Well, light can be created, and so here's a picture of it being created. It's lightning, flash. Light comes from uh, the heated gas in the atmosphere where the electric current's passing through it. You can have absorption. Here, the light's not visible. It's the sun shining down on this black pan, and that light's absorbed by the pan and turned into heat, and so you can fry an egg. In principle, if it's hot enough. This should be in Australia. Um, you can have light transmitted, so what's here, the picture here is a laser that's shining through a particulate like smoke or fog. And so you're seeing the light pass through. Normally, we don't see light pass through an object. And so the picture here would be redundant otherwise. But here we can see the light pass through a material where some of it gets reflected. Light can be reflected or scattered. So we call scattering is when light bounces off an object and it's a rough object and it scatters every which way. We call reflection when the object's uniform enough, light comes in at an angle and bounces off at an angle. So we define what it looks like, but we can ask, what is it? Right? And so people had notions as to trying to figure out what light is. And some people thought that, they kind of understood it was energy moving place to place. And so they thought, well, maybe it's physical objects, what they call photons. That, say an object's glowing, it spits out little particles of light, and then your eye absorbs them and you see the object. And other people thought it's more like waves, like water waves on a surface, like a pond. And they spread out like the waves do. And the wave carries energy and cause things to move, but it in itself isn't. It's something that's waving. And so eventually we get to where we can show that light acts like both. Acts like a wave or a particle. I sent you some links to some different experiments. I sent you the papers. So in the 1800, I think like in 1800, there was a guy, Thomas Young, who built an experiment that ultimately showed light looks like a wave. And his experiment says, let's take a measurement, pass light through a set of gratings, a set of slits, and make it spread out from there, and we see how it interacts. If light's a particle, it just goes basically through these gratings, through holes, and it just keeps going. But waves don't do that. They go and they spread out. And so he saw that they spread out. And that was what's called the double slit experiment. He saw that waves can interfere with each other, and he saw that interference with light. So those waves, they have a wavelength, they have a frequency. The wavelength is between similar points in the wave. The frequency is counting how many times the wave goes up and down per second. And there's a wide range of stuff for light. So at the very longest wavelengths, or the lowest frequencies, are things like radio transmissions. And you go up from there, your microwave, things that are hot. Eventually we see stuff that's glowing, it's visible, visible light. And then it gets even shorter. At very, very high energy, you get stuff like X-rays. And so, effectively, energy increases with frequency. That's kind of an important thing. We talk about some other sources, so you can look at this and say, well, what do we mean by this sort of stuff? Well, is everything gives off light in some way. Everything radiates. And we can associate particular radiations with particular temperatures or particular energies. So light is... So people ask, well, if light is a wave, what's waving? When you talk about water waves, you can see the water move. And when you talk about sound waves, you can't see the air move, but you can tell that it's moving. You can feel it, or you can measure the motion of it. Well, what's waving when light waves? And we define a thing as waving. It wasn't obvious that there is anything that's waving, and it should, light should be able to pass through anything. So we figure out eventually that we'll talk about in physics that there are charged particles and they have electric forces between them. And we ask, well, what carries that electric force? Well, there's a field that these charged particles create that when they interact with other particles, that field generates the force or carries the force. And ultimately, there's an electric field and a magnetic field everywhere. Right? And you can tell that there's magnetic fields. You can hold magnets together and feel them. Or you can, like if you've ever just been very close to getting shocked by an electric shock, you can feel your hair stand on end. You can feel the electric field before the spark happens. And so electromagnetic waves are waves in the electromagnetic field. And so light interacts by moving charged particles around. Waves have a speed. The speed of an electromagnetic wave is the speed of light, which happens to be a constant. It's 3 times 10 to the 8 meters per second. And so you can relate the frequency and the wavelength to the speed. And, we state that here. Everything's moving the same speed, so if your wavelength's long, your frequency is small. All right, so people didn't know that light had a speed. That's kind of an important thing. So in the slides, I talk a little bit about how they figured it out. Is that people originally thought that light basically was an instantaneous effect. And then people realized, well, there might be a speed, and they tried measuring different ways. One way was just having someone stand on a faraway hill, and when you turned on a lantern, they turned on a lantern. And I just measured reaction times. You kind of need very large distances to figure out the actual speed. And so when the Galilean moons were discovered, people could start charting and timing eclipses for the moon going behind Jupiter. So people looked at the timing for Io because it was convenient. It's about a week for it to orbit. And they realized that their predictions when the Earth was on the far side of the sun were delayed compared to on the near side of the sun. And they realized, and in this case, Romer, who's I can try to remember who he was, where he was from, but he was an astronomer who realized that the delay was due to light having to cross the Earth's orbit. And so he estimated the size of the Earth's orbit and estimated the time that it took for the amount of delay. And he figured out that, based on that delay, it took about 10 minutes to cross the Earth's orbit. which gave a speed of about 220,000 kilometers a second, which is pretty good. It's like 2/3 of the right answer. So, and then there's different ways of measuring. You can notice the speed of light as light goes through a telescope that's at an angle. Because the Earth's moving, light that starts at the top can't make it to the bottom. It hits the side of the wall. And so you tilt you have an apparent source and the actual source, which you can tell because the Earth doesn't move constantly in the same direction all the time. And so you can deduce, based on this aberration, how off is a source speed of light. And that's a better estimation, a much better estimation. And then there's different ways of trying to find, basically trying to notice flickering and notice when you've canceled that flickering out because something's rotating at the right rate, which would let you figure out the time for the light beam to pass between two mirrors, or effectively you get better and better measurements by actually trying to time how long light took to move. And eventually it got to a point where we got it accurate enough, you could measure the wavelength of light in a cavity and figure out the speed from that. And we talked about interferometry in the next chapter, but there's different techniques where you could figure out the speed of light through the interaction of light with itself. And eventually people were like, we've gotten it pretty precise. Let's just define it as this, because it's really easier to figure out other stuff once we know what this is. So we define it as this number written down here. But we always tend to round it to a different value. So it's 299,792,458 meters per second. We just say that's it. That's what it is. Well, we effectively define the meter in terms of the speed of light. So one other thing that I should talk about is light has a property that other waves don't necessarily appear to have. I want you to imagine shaking a jump rope. You shake it up and down and you make waves in it. That's fine. But you can shake it up and down or you can shake it left and right. There's an orientation to it. And that's the picture here on the left is you can imagine shaking it where it's constrained to move only up and down or only left and right. Say you run it through a picket fence. And so it'll easily move up and down, but if you rotate the picket fence 90 degrees, it won't do it. So that is what's called polarization, is that it has a directivity, a direction to it. So light can be polarized. Normally, it seems like it's completely unpolarized. But if you pass it through a material, it can polarize it. And so when you do that, you generally lose about half the amount of light. So you've seen this if you've seen sunglasses. Sunglasses are polarized. You can see that they also absorb light. So the top picture is just two pair of sunglasses. Each one absorbs light. The pair of them absorb a little bit more. But these are polarizers. So when you rotate one 90 degrees to the other, the light passes through one. That light's polarized and can't pass through the other one, and it's completely dark. The reason these slides are in the notes is that I typically show this to students. I hand out polarizers, and I show you, other places where you see polarized light. Computer screens and projectors tend to have polarized light of one form or another, and you can detect it. That polarization, the amount of light that gets through a polarizer that is at an angle, the amount of light, the intensity, is based on your original intensity and the cosine squared of the angle. And so the cosine squared of 90 degrees is 0. That's why it blocks. All right, so that's light as a wave. Now, the problem is that people also come up with other experiments that show that it's a particle. I think the one I sent out was the first one. Einstein looked at light hitting on metals. And this was kind of a people have done this. They shined light on metals and they measured the electric current that you could get out of it. And so there was a realization that there were some peculiar things. You'd think that if you just shined more light on an object, that it would produce more electric current, let's say. And it shouldn't matter if it's red or if it's blue light. But what people realized were that you would get more light if it was blue than you would if, there would be a color, a wavelength that wouldn't produce light. Anything below that wavelength, you wouldn't get any light at all. Or anything above that wavelength, you'd get none at all. And then bluer light would create more energy. And this was explained as light being a particle. This was actual collisions of light particles against electrons. And the collision would cause the electric current, but you had to have enough energy to kick the electron away from the atom. And so light had to be a particle. And these experiments don't contradict each other. Right? This double slit experiment says light's a wave. The photoelectric effect says light's a particle. They're effectively both. So photons have a frequency, and because you can pretend while you're saying light's a particle, you can pretend it's a wave, it has a wavelength. But the important thing is the energy, and the energy depends on the frequency. In the example of the photoelectric effect, the color. And so we give these formulas. You can relate the wavelength and frequency to the speed of light, but you can also relate the energy to this other constant, what's called Planck's constant times frequency. And so you can intermix these. All right, you can relate the energy to the wavelength as well, if you want. All right, so what Einstein is talking about when he talks about the photoelectric effect is the interaction of light with matter. So we have to talk about matter. Most of y'all probably took chemistry, I think. A fair number of y'all certainly did. And most of y'all have taken some sort of science class where you know what's going on in an atom. The nucleus of an atom has protons and neutrons. The atomic number is the number of protons. The atomic mass is the total number of particles. Molecules consist of two more atoms. But in an atom, you have basically a cloud of electrons around it, or a cloud of stuff that represents the electron. Electrons are weird. We used to think they orbit like planets, and then we realized that they kind of don't. In fact, they kind of just have a probability of being seen somewhere. They're kind of everywhere at once around an atom, but they've got definite energies. So maybe that's a way of thinking of it, is there's some stuff moving around with some energy around the nucleus, and then the nucleus has the atomic particles. Isotopes just mean that you have different numbers of neutrons, but effectively the same element. Matter comes in phases. You know the three phases: solid, liquid, and gas. There are others, and I'm going to explain that when I talk about temperature. Imagine what happens when you increase the temperature. Right, is you start with ice, let's say. Ice is a nice crystalline structure. You heat it up and you start breaking those crystal bonds and you get a liquid. When you heat that liquid up, liquid has chemical bonds between the molecules, but they're not very strong, and you can break those, when you get it up to, 100. So when you get it up to boiling point, 370 Kelvin, the individual molecules are now separated out, and it's steam. It's a gas. What happens if you keep heating it? Well, you keep adding energy to the molecules. Eventually, you break the chemical bonds. You break the molecules and atoms, what's called dissociation. You keep heating it there, and eventually that energy goes into the individual atoms, and you kick electrons off of it. You ionize it. So you form a plasma. And the more you heat it, the stronger the plasma is. Eventually you get bare nuclei and electrons everywhere in the core of a star. All right, so that's your phase changes. You can, starting at low energy, you can melt and evaporate and then eventually dissociate and ionize. And so there's plasma and, so phases kind of is a weird, you're doing phase changes by breaking up molecules into elements and breaking the elements into their constituent particles. So yes, there's 3 or 4 phases of matter, but in astronomy we mean a different sort of thing for phases. We mean what's going on to the matter when you add more energy, increase the temperature. And the phase is kind of also a little bit, it depends both on temperature and pressure. If you think about a glass of water or think about the ocean, there's clearly liquid in it. There can also be solids in it because you can have ice floating in it. But you'll also have vapor on the surface of it. So you can have, a particular molecule can be part of the vapor, it can be part of the liquid, and it can go back and forth. So often you have several phases around. I mentioned that electrons in atoms have definite energy, and there are some properties to the electron that cause it to have specific states. All right, we're not saying that the electrons are in a particular place, but we're saying they have a particular energy. And the more excited the electron is, the more energy it has. So, the electrons are restricted. It can't be in between. Right? In this picture, like this arrow here and this other arrow are in between states. Those aren't allowed. What this represents is something trying to go from this bottom state, what's called the ground state, up to some other state or away. Well, it can't go to any of these intermediate spots. It's got to go to these particular energy levels. I should have stuck with this. Yeah. So these particular energy levels, this is called quantization. Is you have to have a particular amount of energy to cause a transition between. So what does it mean for an electron to be in a particular energy level? Think of it like kinetic and potential energy. You're storing energy in the electron, and then you can gain it back in some way. So what this does is, when light passes through matter, it interacts. Light is some energy, and you can store it in the energy levels of the electrons. And so what you get is, when you see light, you see a spectrum of light. But you can see that the light is created by releasing that potential energy, or the light is absorbed to store that energy. So spectra are combinations of 3 different types. There's emission spectra. So first, there's a continuous spectra. If something's hot and it glows at all wavelengths, that is your continuous spectra. All right, so there's a continuous spectra. And I think, why did I put this here? All right, so there's a particular spectrum. Here's just a hot light source gives you a continuous spectrum. But if it's caused by transitions between energy levels for an electron, you get very specific wavelengths because they're very specific energies. So you get what's called an emission line spectra. And if you are absorbing light, you start with a continuous spectra and you absorb light and store the energy in those electron energy levels. You get an absorption spectra. You get very particular wavelengths absorbed, taken out of the spectrum. So a continuous spectrum is just all light. It just comes from a hot object. But an emission spectra just picks up those particular wavelengths that correspond with those energy level transitions. And the absorption spectra is the same thing. It's the energy, the emission spectra releases energy, and the absorption spectra absorbs energy. And so every sort of atom has a very unique set of energy levels. And the transition corresponds to a particular energy and a particular frequency and wavelength. So if you can see from an emission or an absorption spectrum those particular transitions, those particular wavelengths, you can deduce the element that was involved in the light. And this is an example. This is hydrogen. You can see the spectrums that go between level 2 and higher levels. And in the blue and purple light is the more energetic stuff, and the red line is the least energetic stuff. And you can see this is an emission spectra. This is an absorption spectra. And so what I would usually do is show you all several different spectra and let you see the particular lines that you would see. So if you were looking, we would see helium, and it's different. And in sodium, basically when you see sodium, you just see that orange paralines. That's why street lights that use sodium, they're basically yellow. And in neon, y'all have seen a neon sign. It's because you're passing current through neon, and it excites the electrons. And when they relax, when they give up that energy, it comes out as orange light. So when we look at these different spectra, we can figure out what types of atoms, what types of ions are available. All right, so this picture that I showed at the very beginning is the solar spectrum. And there's all sorts of different lines in here, but you can distinguish the different elements by their particular lines that you can see. So there's other ways for energy to be stored. If you have a molecule, molecules can rotate and they can stretch, they can vibrate. And so that gives you additional energy levels. So there's lots of information in determining from the spectra what's going on with a thing. Right, so spectras can be really complex, but you can study and focus and tear them apart. All right, so I talked about hot objects glowing. I do have to talk about thermal radiation. Most objects emit thermal radiation. I mean, basically everything. And the thermal radiation only depends on temperature. This is distinct from the atomic transitions. This is just, it's a hot object, it glows. So I asked y'all to go through this black body radiation activity, but effectively what you'll get out of it is hotter objects emit more light at every frequency, but they also emit bluer light, which is higher average energy. And so we can use that when we study stars. We'll say, oh, we see red stars. They're less energetic, and they have a lower temperature, and blue stars are higher temperature. And so when we look at a spectra, we can tell what created the spectra. All right, and this particular one, we're going through the examples. This is reflected sunlight. So some of the blue light gets absorbed, and the object looks red to us. We can see thermal radiation. This is an infrared spectrum, has a peak, and it's telling us it's about 220 Kelvin. That's kind of a cold thing, so it's not necessarily anything on Earth. There's carbon dioxide, and this is an absorption spectra, so it's light passing through carbon dioxide. So it's like an atmosphere around a planet. There's ultraviolet emission, which means there's something ionizing or exciting electrons in the gas, and we're seeing that ultraviolet light from it. And what we can piece together from all that is that this is a spectra for light from Mars, which kind of makes sense. It's a red object, so blue light gets absorbed, and it's got a carbon dioxide atmosphere, and it's fairly colder than Earth, and it has a hot upper atmosphere. So we'll go more detail in a couple of chapters for that. So there's a couple more bits. When we measure the wavelength of light, that is kind of relative in the sense of if we're moving, we can measure a different wavelength than if it's stationary. You've heard this. If you've heard a siren go by, it increases in pitch as it approaches you and decreases in pitch as it drives away from you. And that's what we get. We talk about this train in the picture. Two observers can hear different wavelengths, but they're doing that because the train and the source of the sound is getting closer to one of them. And light does the same thing. If the light source is moving toward you, it looks a little bluer. And if it moves away from you, it looks a little redder. And we can see that. If we see a spectrum in the lab, it looks stationary. But if it's moving away, it shifts redwards a bit. And if it's moving toward you, it shifts bluewards a bit. This is what's called the Doppler effect. If you've heard the weather on the nightly news, and they talk about Doppler radar, that's what they're talking about. They're measuring the shift of light they send out and light that reflects back and deducing the speed of the thing that reflected it. So we can measure Doppler effect, and it tells us information about the speed of the object moving. It only tells us stuff that's moving toward or away from us. It doesn't tell us anything about motion across across our field of view, just toward or away from us. And if we want to calculate it, we can. We have a formula for it. If the speed's not that big, it looks like the formula we have here in the slides. I'm not sure why I have different slides here, but that's okay. If it is particularly fast, then you can correct for the formula. There's a correction term, but that's not important right now. Doppler shift can do other things, right? If an object's rotating, one side of the object's coming toward you and the other side's going away, you can see a Doppler shift in the light. And so you get effectively how broad out is the light. It tells you how fast the thing's rotating. Right, and that's what you see here is that when these objects are rotating, the bottom side is going to be red because it's going away, and the top side is going to be blue because it's coming toward you. The faster it rotates, the broader out, the bigger the difference between the blue shifted and red shifted light is. All right, so that's light. That's the big things I want to point out is that we study a lot with Doppler shift and a lot with spectra because we're, in astronomy, the biggest thing we do is try to observe light. And yeah, we can get the positions of objects in the sky, but we also want to figure out what they are. And to figure out the matter, we kind of have to figure out how light interacts with it. So when we take measurement of light, we're not just looking for positions. We're not trying to build images. We're also looking at the spectra. So chapter 6, the next chapter, we will go in detail over how do we get information out of light. All right, so I'm going to let the video conclude here. All right. Yeah. All right, that's it.